So far in this module, we have discussed the concept of normal and shear stresses. And we have seen that normal stresses arise when you have normal forces acting perpendicular to the cross-section of a specimen. And shear stresses arise when you have a force acting in the plane of a cross-section. They also give rise to strain, which relate to the elongation and contraction of the specimen. We have also seen how to relate stresses and strain via stress versus strain plots. And we have seen that for ductile material, we have something like this, where we have an onset of yield, and that is defined by a yield strength point, and then we have ultimate stress that ductile material can endure. So this is for the ductile material, that's sigma versus epsilon, ductile material. And then we also have sigma versus epsilon plot for brittle material, where basically we have a fracture, so there's no onset of yielding. So this is for the brittle materials. Okay, but if you recall, we started this module by the motivation that we wanted to design structures in the machines that would not fail. So we wanted to see what the limits were, how much maximum force could be applied on something before they would fail. So that brings us to the last point, which is the failure criteria. And the failure criteria would be different for different kinds of problems and what your objective is. So for example, for the ductile materials, your failure criteria could be that your stress should not go beyond the yield point. Okay, so if you say that I have a rigid body and I'm going to apply certain kind of forces on it, as a result it's going to experience certain kind of stresses, and I don't want my stresses to exceed beyond the yield point, because beyond the yield point my material is going to start deforming plastically, and that is not acceptable to me. Then your failure criteria would be the yield point. On the other hand, if you say that it's okay for my material to actually plastically deform, but it should not fracture, then your failure criteria might be based on ultimate tensile strength. For brittle material, of course, you don't have a choice. You basically have to go by the maximum stress that the material can endure. Okay, so to give you a simple example, so let's say I have a wire, and this wire is under tension, and that tension is given to you as, let's say, I don't know, 300 Newton. And we know the diameter is, let's say 1 millimeter. Okay, so that's the diameter. So in this case, it's clear that at every cross section of this wire, we will have only tensile stresses defined as T divided by area. Tension is 300, area is pi d squared over 4. So that's 300 divided by 3.14 times diameter is 1 into 10 power minus 3 square divided by 4. So I'll bring 4 over here. So let's see what this the sigma is. Okay, so let me punch in the numbers, and I get 1200 divided by 3.14, and that is equal to 382.16 into 10 power 6 Pascal. So that's actually 382.16 megapascal. Okay, so that's the stress, the normal stress in the wire. Now, if I told you that this wire was made of some grade of steel, okay, so one of the grades of the steel, structural steel, is ASTM A36. So ASTM stands for American Society of Testing of Materials, or something like that, and they have different designation for different kinds of steel, as well as other alloys like aluminum and so on. And for ASTM A36, the ultimate tensile strength, the sigma U over here, and I think your textbook writes sigma U as SU, is close to 400 megapascal. Okay, it's close to 400 megapascal. So if your failure criteria was based on the ultimate tensile strength, so in a sense you're saying that I don't want this wire to break. It could yield to some extent, but I don't want it to fail. I don't want it to get fractured, which means that if you are going to guard against a fracture, you have to look at the sigma U as your sort of the limit. Okay, so if you compare this with this number over here, you can clearly see that we're going to be more or less safe because we still haven't reached 400 megapascal, but it is still problematic because you're approaching that sigma u, and any kind of defect in the wire could actually lower the actual value of the ultimate tensile strength. On the other hand, if your failure criteria was based on plastic deformation, then sigma y, of course, is much smaller in this case. So I don't know what that number is, but let's say sigma y for this was given as 350 megapascal, then clearly sigma is more than sigma y, sigma is less than sigma u, and if this was a failure criteria, then you would say this has failed. And if this was a criteria, then you would say that, well, it is still safe to some extent, right? It may not be always, but at least in this case, it looks like it will be kind of safe. So this is a very simple example. Now, this particular section in the module is about structural analysis for engineering design. So I want to demonstrate all this by a very simple engineering application. So let's say we have a problem where we have a flower vase and we want to hang it using a wire, right? So I have a wall, all right, and I'm going to take a hinge joint. So I'll create a hinge joint and I'll have a bar, all right, and I'm going to have this bar tied to the wall via a cable. Okay, and right here, I have a little hole, let's say, and I can hang my vase, and these are my flowers, let's say. All right, and the vase has certain load. It has to take certain amount of load. Okay, so let's say it's close to 50 kilogram. That's the mass of the vase. And I'm trying to design this entire contraption where I have the bar, I have the wire, and I have a certain load applied at a point, right? Now, there are several questions when you want to design, several questions that you have to answer before you design something like this. So we have the question of the bar. So if you look at the bar, then the question is, what material should be made of, right? What should be its geometry? And that could include the question about the length, the if it is cross-sectional area is rectangular, then we would talk about its width and height, right? Then we have the question of what should be its angle from horizontal. In this case, it's shown to be completely horizontal, but it didn't have to be that way. Okay, same kinds of questions exist for the wire also. What kind of material the wire should be made of? What should be its diameter? Right, because the larger the diameter, we know the normal stress would be less. What angle it should be making from horizontal, so what is that angle, right? So there are all these questions about the wire. You could also have the question about its length. Okay, then we also have the question about these joints. So this is a joint, right? So this joint over here is a pin joint that we have picked, but it could have been a cantilever joint. Maybe if you picked a cantilever joint, then you may not have to use a wire. That's a possibility. But is it a pin joint? Is it a cantilever joint? Or is it an adhesive, let's say? It could be an adhesive. So there are all these questions that we have to answer. And that's why design opens up all kinds of possibilities as to what you can do and what you cannot do, right? But let's say our focus for this particular problem is just on the wire. Okay, we are interested, we already have a bar, it was lying somewhere in home and I wanted to just use it, and I connected via a simple hinge joint over here, and now I have to just go to Home Depot and get my wire. Okay, so now the question is, what kind of stresses are exerted on the wire? Okay, now as far as the bar is concerned, things are fairly straightforward. If you look at the bar, if you draw a free body diagram, assuming that this is basically a cylinder bar, which means it can only take forces in the longitudinal direction, either it would be in tension. Okay, now if you look at this picture, this diagram over here, by just looking at it, you may not be able to tell whether the bar is going to be under compression or it's going to be in tension. But that's where the free body diagram and equilibrium analysis comes in and will help you answer those kinds of questions. So the bar could be under tension or compression. So if it's in tension, it could fail in two different ways, right? So it has two failure modes. So one failure mode is the yielding, right? So it could yield. That means that there is permanent plastic deformation, and that may not be necessarily a bad thing, because if that happened, essentially your bar is going to bend like this, and your weight or your flower vase is going to come down to some extent, and that gives you some signal that maybe your entire structure that you put together is going to fail over time. So it's time to actually look at it and do something about it, right? The second failure mode could be that the bar actually fractures. Okay, but it breaks basically, and that could be, bad. I mean, it could be catastrophic. God forbid, if somebody was standing right below the flower vase and your bar failed because of the fracture, then it could be a problem, right? So those are the two possibilities. It could fail in yielding or in fracture. That happens when it's in tension. But the bar could also be in compression. So the bar could also be in compression. And again, we'll find that out from the free body diagram and equilibrium analysis. So if the bar is under compression, then its failure mode is basically what we call buckling. So it will buckle. So it will basically, bend out of shape like that. Okay. Now, as far as the wire is concerned, which is where our focus is, so if you look at the wire itself, wire can only take a tensile load. It cannot take a compressive load. We have seen that before, which means that it can only fail either via yielding or it can fail via fracture. And those are the two possible, failure mode for the wire. All right. So now, how would we know when the wire has failed? Let's say we are guarding against the fracture. So in that case, we want to make sure that in the wire, whatever the normal stresses exist are less than or equal to, or maybe we don't want to say equal to, but strictly less than the ultimate tensile strength. Okay, so L sigma should be less than SU. Okay, so assuming that this is made of some material, let's say aluminum or steel, for which we know S sub U. Okay, so that's our failure criteria. So we're guarding against the fracture in this case. So just to give you some numbers, we have already seen that for different kinds of material, we have a different kind of ultimate tensile strength. So let me draw a table. So materials, and then we have the S sub U, which is your ultimate tensile strength. We have already seen that for ASTM A36, which is a grade of structural steel. So a structural steel, it's close to 400 megapascal. So that's close to 400 megapascal. Okay. Then you have another grade of steel called ASTM, and these are some of the popular grades called A514. Okay. ASTM A514 is much stronger, and it has close to 825 megapascal as the ultimate tensile strength. For aluminum alloys, there's a whole range, of course, because there are different grades out there. It's close to 110 to 480 megapascal. All right, so these are some of the basic numbers, but this is just to show you what are some of the ballpark figures for different grades for steel. Okay, so there's a question of which structural steel grade should we pick. Should we pick ASTM A36 for the wire, or should we pick A514? Or if you're going to go with an aluminum wire, then which kind of aluminum alloy grade that we should be picking. Right. So the first question we have to answer is, what is the stress in the normal stress in the wire? Okay, so if we know that, then we can compute whether this is going to fail or not, right? So let's say we are going to phrase this question in a slightly different. So let's say first question is how much force is needed to break a wire. Let's say we pick some diameter. So let's say of diameter 1 inch. 1 inch is fairly thick, I would say, of ASTM A36 steel. Okay, so our question is, what is the force needed to break a wire of this diameter of 1 inch of ASTM A36 steel? Okay, so we know that when the normal stress is equal to the ultimate tensile strength SU, then the wire is going to break, because after that there is only fracture that is going to happen. Okay, now remember, SU is not equal to the stress at the fracture point. Fracture stress point is actually much lower than ultimate tensile strength point. So sigma is defined as F over A. So F is what we're looking for, and A is pi d squared over 4, and that equal to S sub U, which is 400 megapascal. Okay, so F would be equal to 400 times 10 power 6 times pi. D is 1 inch, so I'm going to convert that into SI system. So 1 inch is equal to 2.54 centimeters. So that's 2.54 centimeter. That's 10 power minus 2 in meters. divided square divided by 4, right? So this is the diameter, remember that too. So if we compute this force, so you know how much that is, let me put in the numbers and see what we get as a result. So we have 2.54 divided by 4 into 400. So I get actually 645.16 into 10 power 2 newtons, right? That's times Newton. So this, I will write this right different, 6.45 into 10 power 4 newtons. So that's the force, okay, that is needed to break this particular wire, right? So this is one question, and I could, you know, sort of phrase a different kind of question. So a second question I can phrase is, you know, this is related to what we have done so far, but you know, in a different way. What should be the radius or the diameter of an ASTM A36 wire so that it can support a load of let's say this is 2000 pound force. Okay, so now instead of working in the SI system unit, let's see if we can do this in the USCS system as well. Okay, so in the USCS system, we know that we can convert the 400 megapascal, that's the ultimate tensile strength. So SU is equal to 400 megapascal, and if you convert that, I've already done this, this is equal to 58,000 psi. Okay, so that's you know, I can write it psi. I can also write it as pound force per inch square, right? So I could write it that way. So that's S sub U in the USCS system. Okay, and we're looking for the radius. Okay, and the load is 2,000 pound force. So what is the stress? Stress is equal to force, which is 2,000 pound force divided by the area, right? And that's area is what we're looking for, and we'll compute what that is. So when sigma, the stress, is equal to S sub U, then we know the wire is going to fail, right? So we're looking for, you know, what should be the radius so that it gets to that point. So this is equal to 58,000 psi, right? So we get A equal to 2,000 divided by 58,000 psi, right? So this is going to give us the area in inch square, right? Because we have psi over here. So if we compute the area from this, and area we know is equal to pi r square, so the r would be equal to 2,000 divided by 58,000, right? So that's that divided by, you know, pi over here, and then finally we do a square root because we're looking for the r. So if you punch in the number in the calculator, let's see what we get. So I get close to 0.105 inches. Okay, so that's what I get. So I get 0.105 inches as the radius. Now, once you get this radius, what do? Well, you're looking to design your contraption. So you go to Home Depot and you say, hey, you know, I need a radius 0.105 inch wire of ASTM A36 steel. Well, you may find that actually you don't have a wire of that size because manufacturers don't make wires in every single size. They make them in some standard sizes. The second problem is that you know, there's practically no factor of safety over here, right? Over time, the wires can get rusted, or the load could increase over time. So there's no factor of safety whatsoever in this case. Essentially, as soon as your load is close to 2,000 pound force, your wire is going to break, right? Almost when it gets to 2,000 pound force. So clearly, design wise, there's a lot more that could be done with this. So let's talk about factor of safety a little bit. So factor of safety. We will use eta to designate factor of safety, and is defined as the design load divided by the rated load. So what does it really mean? What does design load mean and what does the rated load mean? So let me give you an example. If you have ever been inside an elevator, you may have seen signs saying that, this elevator is rated for, let's say this is the elevator, there might be a sign saying that this elevator is rated for 20 people, okay, 20 people or 2000 kilogram, no more than that, right? So that's the rated capacity of the elevator, right? So it tells you that no more than 20 people on average may be weighing 100 kilogram or 2000 kilogram of the total weight inside the elevator should be allowed. Now that does not mean that the elevator is actually designed for only 2000 kilogram, because that could be catastrophic. You can never control how many people really enter the elevator and who weighs what. So if the entire weight of the elevator went beyond 2000 kilogram, does it mean that the elevator is going to fail? Of course not, right? So that's your rated load. So over here, this thing is called rated load. 2000 kilogram is the rated load. Now, factor of safety allows you to create your design in a way so that even if your actual load exceeded the rated load, you will still have some buffer, okay? So if let's say the factor of safety was 2, then the design load would be 2 times of the rated load, right? So for, let's say, the elevator, if the factor of safety was 2, industry standard is, I think, 4. Then for the elevator, of course, the industry standard for different kinds of product changes depending on the application and the use. Wherever there is human life involved, there is a higher factor of safety compared to other applications. So in this case, F design is equal to actually 2 times 2000 kilograms. So that's actually designed for 4000 kilograms, right? So this is the formula that you need to remember. Design load is always going to be higher than the rated load, and it'll be multiplied by the factor of safety. So when you are designing something, you basically take the design load, and that's the number that you use to compute your stresses and compare it with the ultimate tensile strength if your failure criteria is fracture, or compare it with the yield strength if your failure criteria is the yield point, okay? So if let's say we wanted to solve the same problem, the question 2 that we did over here, okay, but now we want to do it with a certain factor of safety. So let's say our factor of safety was 4, okay? So we want to repeat that question. So question 3, we want to repeat, but now eta is given to us as 4, and we have to pick the radius from some standard sizes. Let's say the R is given as 0.125 inches. It is given to you as 0.25 inches. So in the increment of 0.125 inches, right? So 0.25 plus 0.125 would be 0.375 inches, and so on, right? Remember, here we computed 0.105. Now, we're looking at the numbers above them, okay? And we have to pick from one of these standard sizes while keeping the factor of safety as 4. So the first thing you will do is you will use this formula to find what your design load is, okay? So this 2000 pound force over here now becomes your rated load. It's not the design load. So what is the design load now? So the design load would be equal to 4 times the rated load, right? So rated load is 2000, so that will be 4 times 2000 pound force, and that is 8000 pound force, right? Now rest of the stuff will be same. So we already know what our S sub U is. So S sub U is equal to 58,000 psi, and that would be equal to the stress. So the stress now would be F design divided by the area, right? So F design here is now 8,000. So if you compare with the previous example, you see over here the force was only 2000, but now our force is 8000 pound force because we're designing for 4 times of that force. So we will get our area as 8000 divided by 58,000. So you can see that in this case the area is going to be actually what, 4 times, right? So this is A1 and this is A2, then you can see that A2 would be 4 times of A1 because the denominator is same, only the numerator has changed from 2000 to 8000, right? So you would compute your radius on the basis of this, okay? So if you compute the radius, because the area is 4 times and area is pi r squared, so it will be actually square root of that, so it will be the radius is actually going to double. So the radius, new radius R2 would be twice of R1. So R1 is this radius. That'll be 0.210 inches, right? So that will be your new radius. Now, of course, 0.210 inches is not one of the radius that is given to you. So you'll go for the next higher one, that's 0.25 inches. So the radius that you will pick, so let me call it R selected, would be equal to 0.25 inch. Right? So essentially we have asked three very simple questions over here, starting with what is the force needed to break a wire, and the second one was what should be the radius, and the essential formulas are same, and then the third one where we introduce a factor of safety. Now let's go back to our original problems. Our original problem is basically analysis of this, right? So let's see how we can find out what should be the properties of the wire that we need to pick here.